In this series, we're trying to build a vacuum tube computer, and it's kind of loosely based around the Motorola MC14500, which is a little 1-bit microprocessor. However, in the previous episode, we took a look at some of the shortcomings of the Motorola chip. Most notably, it has only a logic unit. It doesn't have any arithmetic functionality. And so we did a massive redesign, giving it arithmetic functionality, making it a proper ALU. And we did all of that constrained within the confines of the actual 1-bit architecture. So I'm really excited about this new design, and I think we can now officially call it the Usagi Electric 14500 or the UE 14500. So it's our microprocessor. But everything that we've built up to now, as fantastical and wonderful as it looks, is really just built around 2 or 3 fundamental building blocks. I mean, these are really simple building blocks. We're just kind of combining them in ways to achieve this interesting functionality. But in order to facilitate further, more complex functions on the microprocessor, we need to expand our building blocks by 1. And so that's what I want to do today. I want to hop over to the bench, take a look at what our building blocks that we've been using up to now are, take a look at how we're going to expand it, then build it out and test it. So let's hop over there and get started. All right, so this is the gate level representation of the microprocessor that we're trying to build. So far, we've built the instruction register, the skip, as well as the instruction decoder. Now, in this version of the logic diagram, I've actually gone in and I've added buffers to the outputs in all the places where we've added them so far in everything that we've built, as well as in places that I think we're going to need them in the future. And so in the previous episode, we had 16 individual cathode follower buffers that we attached to the 16 outputs coming from the 16 NOR gates that made up our instruction decoder. Now, looking at everything that we've built so far, this huge collection of stuff over here, you'll notice that there's pretty much only 3 primary building blocks going on. We have OR gates, we have NOR gates, and we have buffers. So let's take a look at how we built these 3 different logic gates using vacuum tubes. And this is pretty much it. Everything we've built up to now is a variation of what you see right here. It's incredibly simple. So we'll start with an OR gate, and we're building the simplest of simple OR gates by just using 2 diodes. So we have our 2 inputs coming into one end of the diodes, and then the output of those diodes are tied together, and that gives us our OR output. So if both inputs are low, our OR output is low. But if one or both of the inputs go high, our output goes high. And then a NOR gate is just an OR gate with its output inverted. So we take our output from our OR gate and we send it into our 220K by 220K voltage divider network here that goes to minus 12 volts. And then we have a little 4.7K resistor coming off of the center to our grid. And so if both A and B are low, the minus 12 volts pulls the grid to a negative potential, and that blocks any electrons from flowing through the tube, and then the plate is pulled up to 24 volts through this 33,000 ohm resistor here. If one or both of the inputs go high, it now pulls our grid to a higher potential, which allows electrons to flow from the cathode to the plate, and that pulls the plate down to a low voltage level. And so that's how we get OR and NOR. Now, whenever our NOR gate is at a high logic level, which means that our output has been pulled up to 24 volts through this 33,000 ohm resistor here, we don't have a whole lot of current available because this 33,000 ohm resistor is quite large, especially with such a low plate voltage. With just 24 volts, the amount of power that we can pump out of this output is incredibly limited. And there are some situations where one NOR output needs to feed multiple inputs, which means that it's going into multiple voltage divider networks like we have on the input over here of 220K and 220K. And if you put enough of those in parallel, it's going to pull our NOR output voltage too low. So that's why sometimes we need to buffer the output. Now, a cathode follower buffer is very similar to the inverter that we just looked at, except that the output comes off of the cathode instead of the plate. And instead of the plate having a large resistor, it has an incredibly small resistor, and now the cathode has a large resistor. So if we have a logic low coming into input A here, that puts the grid at about 2 volts. So if the potential of the cathode is below 2 volts, electrons flow, bringing the potential of the cathode closer to that of the plate, which is essentially being held at 24 volts. Now, if the potential of the cathode goes above 2 volts, well, now the grid is negative in relation to the cathode, and so the electrons stop flowing. And so essentially the cathode follows the grid around, hence the name cathode follower. But the benefit of this is that the only thing impeding the current coming out of our output is the internal resistance of the tube, which for the 6AU6 is about 2000 ohms. And 2000 ohms gives us a much stronger output than the 33,000 ohms that we saw on our inverter. So with just these simple building blocks, we've been able to create quite a lot of functionality. So if we take a look at our entire logic diagram again, you can see that the majority of it is NOR gates, OR gates, or buffers with the occasional inverter thrown in. And we can build all 4 of those using the building blocks that we just looked at. But there's one more gate in use here that we haven't had to build yet, but we're going to have to soon. And that is the NAND gate. And you can see it in a couple places, but in particular, let's take a look at the input enable register, which is right here at the top. Now, at the heart of it, the input enable register is just a D flip-flop made out of 6 NOR gates. This is exactly the same design that we used for the 4-bit instruction register. So that's fantastic. We've got the large majority of the input enable register already figured out. Now, the clock that comes into this D flip-flop has 2 requirements. 1, it needs to be inverted, and 2, it needs to be gated. I only want the clock to operate when our instruction coming from the instruction register is 1010. That is the input enable instruction. And so gating a clock like this is really easy. You just have a NAND gate. And the way that a NAND gate works is that the output is high unless both inputs go high, at which point the output goes low. So we have our instruction 1010 coming into one input of our NAND gate, and we have our clock coming into the other input of our NAND gate. And so the clock can toggle up and down all it wants, but it will not affect the output unless our instruction of 1010 is high. And then if that instruction is set, whenever our clock signal goes high, the output coming out of our NAND gate will then go low. And that will initiate our D flip-flop to store whatever data is being input into the data pin here, which in this case is coming directly off of the 1-bit data bus. And then looking at the output of the input enable register, you'll see that we have a NAND gate, an inverter, and then a buffer. And so the reason that we have it set up like this is that we actually need an AND gate here. And so a NAND gate is an AND gate with its output inverted, so we need to re-invert that output one more time to get it back to being an AND gate. And the reason we want an AND gate is that we only want the data from our 1-bit data bus to make it to our output whenever the input enable register is on. And so this seems a little strange to have a NAND gate with an inverter after it, because wouldn't it make more sense to just have an AND gate going directly to the buffer? Well, yes. But in this situation, it has to do with how we're building our NAND gate. So let's take a look at how we're doing that. So just like the NOR gate, we're actually building an AND gate with diode logic, and then using a vacuum tube to invert and amplify that AND gate output. And you can see that we have 2 diodes that are facing in the opposite direction that they were when we were looking at the NOR gate. And those diodes are connected up to 220,000 ohm resistors that go to negative 12 volts. And then in between that 220,000 ohm resistor and the diode is where our input comes in. Now the other side of those diodes are tied together and then have a very large resistor pulling them up to 24 volts. And this point is our AND gate output. So how does that work? Well, if both of our outputs are low, the 220,000 ohm resistor that goes to minus 12 volts is a much smaller resistor than the 1 mega ohm resistor that goes to plus 24 volts. And so those resistors are acting as a pull down for that point where we're taking our AND output. However, if we put a logic high into one of the inputs, for example, input A here, that logic high input acts as a blocker for the negative 12 volts. However, the diode doesn't let that logic high input make it all the way up to our AND gate output up here. But the other diode is still connected up to negative 12 volts through the 220,000 ohm resistor, so it's still pulling our AND gate output low. But if we put a logic high input into both input A and input B, we now have a logic high input acting as a blocker for both of the diodes. But because the diodes are situated the way they are, that logic high doesn't flow up to the AND gate. And that's why we have this 1 megohm resistor up here. It acts as a pull-up for our AND gate output. So when both of our inputs are blocking the negative voltage, the 1 megohm resistor pulls our AND gate output up to a high logic level. And so that's how we created an AND gate. This is brilliant. It's really nice. Except that the 1 megohm resistor is massive, which means that we have an incredibly small amount of current coming out of our AND output. So to ensure that our output is nice and strong and gives us clean logic high and logic low levels, we take that AND output and we run it into the grid of an inverting amplifier vacuum tube. Now this inverts the output, giving us a NAND gate, but we have a NAND gate now with clean logic high and clean logic low. Now this is a very cool circuit and it seems like it should be pretty easy to build, so let's pull out the breadboard and give this a quick test. All right, I've got my breadboard set up exactly like the schematic below it. I've got my 4 220,000 ohm resistors right here, creating this interesting resistor network on the input here. And then I've got my 2 diodes here and my 1 megohm pull-up resistor. And this is the AND portion of it. And my 2 inputs, A and B here, are going to be these 2 little push buttons here. And then I just have a 6AU6 set up as an inverter over here. And I've got a little VFD that should display the output of it. So it should be on unless both buttons are pushed. And then over here on the far right, I've got my little regulator that's going to drop the 24 volts input down to 6 volts just to power the tube here. So let's flip the switch on and give it a shot. Now the moment I flip the switch on, this VFD should turn on and then stay on until both buttons are pressed. Yeah, there we go. The VFD came on immediately. That's awesome. All right, let's give it a test. Let's push one button. Yeah, nothing happens. That's good news. Let's push the other button. Okay, nothing happens. That's good news. So moment of truth. Let's push both buttons and the VFD should turn off. Yeah, look at that. We have a NAND gate. How cool is that? So we've built essentially a diode logic AND gate, and then we're able to invert that output and turn it into a NAND gate. That's awesome. That's going to be extremely useful. So now that we know how to build a NAND gate and we have an idea of some of the places where we want to use it, let's take a look at the overall microprocessor layout and figure out what PCBs we want to build next. All right, so what I want to build today is I want to build the input enable register and the supporting logic that goes around it. But just by looking at this logic diagram and looking at what we've built so far, we can tell that it's laid out quite differently. So instead of looking at the individual logic gates, let's take a look at how I'm planning to lay out the actual boards themselves. And this is my current design idea. So this big group on the top is what we've built so far. That's the skip with the instruction register, with the decoder, and then all the buffers necessary. So I'm imagining a slim strip of boards that act as kind of an interconnect between the instruction register up top and the arithmetic logic unit that's going to go below it. And part of this interconnect, aside from just moving a whole lot of signals in certain directions, is going to be our input enable register and the control logic for it. And this control logic is actually the one that I'm really mainly concerned with, because this is going to be those 2 NAND gates and the inverter to make it an AND gate that we just took a look at. And so we need to build this up on a PC board. And it just so happens I've already done that. So I want to test this out today. So let me get this piece of paper out of the way and we'll give this a proper test. Well, this is the board that I want to test out, and it has a NAND gate here for our clock input, a NAND gate here for the IE in output that goes into an inverter, and then we buffer it. So these are those 3 gates that I was talking about earlier. And so I really want to test these out. But just testing them out like this doesn't really let me know if they're going to work correctly with the input enable register in place. So we need to get the input enable register in here as well. So it just so happens I already made up one of those. And then to connect these two to each other, I need a little board that goes right in the middle. So I've got one of those right here. All right, so now we've got our input enable control and our input enable register. Oh, but I would like to have a visual indication of whatever's being stored in the input enable register. So we need a little bit of a display for that. So I've got this board cut up for that as well. All right, and so what this does is it takes the inverted output of the register, brings it in, inverts it, and then buffers it. And then this little VFD is our display that lets me know what is stored in the input enable register. But in order for this one to work, the output of the input enable register, which is here, needs to come over to the input over here. So I've got another board specifically for that. All right, so we're getting pretty close to being able to test this, but we need to now sort out the inputs into this one. And we have 4 separate inputs that we need to figure out. For our first NAND gate right here, which is going to be the clock signal that initiates our input enable register over here, we need the actual clock coming into it as well as the instruction register control line 1010. And 1010 is going to come down from way off to the right and snake across the top of all of these boards. So I need another little board here to bring that 1010 along with a few other signals on over. So we'll go ahead and plug that board in. All right, and then I've got to get this 1010 signal down to here. So that's what this little board here is for. And this top board here also carries the input enable register signal all the way back over to here, because that input enable register signal is also being input into this other NAND gate here. Now the final input that we're missing is the data from our data bus. And that's actually going to come from our end piece, which has a bunch of connections on it. All right, so I think we're in a pretty good place to give this a proper test now. But there's still a couple things that we need to actually hook up in order to do the test. So I'll go ahead and hook up my breadboard here for that. All right, so our breadboard is set up pretty simply. We have our ground power and minus 12 volts coming in here, and then that goes through these jumpers over to the main inboard here that's going to end up powering everything here. And then we have this toggle switch on the left, which is going to be our data. And then we have this push button here, which is going to be our clock. And then we have a toggle switch on the right here, which is going to be our instruction register 1010. So in order for a 1 to be stored in the input enable register, both 1010 and the data need to be set to on when I toggle the clock. So let's go ahead and give this a test. We'll flip the power switch on and we'll see what is stored in the D flip-flop based upon this VFD here. Okay, I think everything is now warmed up and ready to go. I can feel that some heat getting into the tubes here. And our VFD is off, so hopefully that means that the input enable register just initialized with a 0 in it. So let's check. If I push the clock, nothing should happen. Yeah, okay, so that's good. Okay, so let's turn our data toggle switch on. So now we have data coming in, but our 1010 instruction from our instruction register is off. So even if I hit the clock, we should not store anything into the input enable register. Yeah, that's good. Okay, so nothing happened. And vice versa as well. If I turn 1010 on, but our data is 0, yeah, nothing gets stored in there. So here we go. Moment of truth yet again. Both our data is on and our 1010 instruction register is on. So if I hit this clock, we should see this VFD illuminate, which tells us that we're now storing a 1 in our input enable register. Yes, look at that. Awesome, our VFD kicked on. So now we know that our input enable register is storing a 1. So this is really cool. We built essentially half of the interconnect that's going to connect the instruction register that we've been working on in the previous episodes with the logic unit and the arithmetic unit and the result register and everything that's going to come below this. Now there are some bigger problems that we're going to have to deal with. You may notice that I decided to test this one by itself. And that's because the instruction register and decoder and all of those boards are now pulling so much power that I'm afraid to add more tubes to it without actually first building a kind of soft start so that our inrush current can be something that we're more prepared to handle. But I want to finish this interconnect board out first, and then we'll get to work on figuring out a soft start system for it. But for now, this is awesome. I think it looks really cool. I love the fact that I've got another one of these VFDs in the circuit. The more of these I can stuff into this, the better. But for now, I'm going to keep playing with this, pushing buttons, turning things on and off, because I think it's just so much fun. So thank you guys so much for watching, and we'll see you in the next episode.